Here we have to use the rational zeros theorem to find all the real zeros of the following function. Then we're going to use those zeros to factor f over the real numbers. So the rational zeros theorem says that if we take all of the factors of q, our last term, and divide them by all of the factors of p, the coefficient of our leading term, then we'll get all the possible rational zeros. So the factors of 68, if we do a factor tree on 68, it goes in 2 times to make 34, and 34 breaks down into 2 and 17. So we have the possible p over q's would be anything plus or minus 1, 2, 2 times 2 here would give us a possible 4 and 17. And 2 times 17 is 34, and 4 times 17 is 68. So those are all the possible numbers that could divide into 68. In the denominator, we would just have all the possible factors of 2, which thankfully is just 1 or 2. So this gives us all of the possible following numbers. P over Q could be, in any positive or negative combination, 1 over 1 is 1, 2 over 1 is 2, 4 over 1 is 4, 17 over 1 is 17, 34 over 1 is 34, and 68 over 1 is 68. Now each of these numbers now needs to be divided by 2. Also, we could have 1 over 2 as 1/2, 2 over 2 we already have as 1, 4 over 2 we already have as a 2, 17 over 2 we don't have listed, 34 over 2 we do have listed as 17, and 68 over 2 we do have listed as 38. So those numbers right there, positive or negative, 1, 2, 4, 17, 34, 68, 1/2 and 17/2, these are the only possible rational zeros. The way we figure out which ones actually work is usually we use synthetic division. Now let's be kind on ourselves and start at the beginning. I like to start with 1s or 2s. So I'm going to try x equals 1 first and divide this using synthetic division into the polynomial for 2x cubed negative 4x squared negative 34x and 68. I know this works because in my last term here that should be a remainder, I'll get a 0 if 1 actually is one of our zeros. Okay, let's start. So bring down the 2. 1 times 2 is 2. Add vertically, negative 4 plus 2 is negative 2. Negative 2 times 1 is negative 2. Add vertically, negative 34, and negative 2 is negative 36. And 1 times negative 36 is negative 36. But here when I add, I definitely don't get 0, I get 32. So I know that x equals 1 is not a 0. Okay, let's try x equals 2. So I'm just going to work my way through this list until I get a hit. So if x equals 2, I'm going to do 2, negative 4, negative 34, and 68 again. Do synthetic division, bring down the 2. 2 times 2 is 4. Negative 4 plus 4 is 0. 2 times 0 is 0. Negative 34 plus 0 is negative 34. Ooh, this is looking fun. Negative 34 times 2 is negative 68. Yay, which is a 0. Okay, that means since I got a 0 in the remainder spot, that means that x equals 2 is one of my zeros. So that means that when I'm going to factor f of x, I know it factors in part to x minus 2 as one of its factors. I also know the leftover portion is given by this. Okay, so remember it goes remainder, constant term, negative 34. This would be 0x, but I'm not going to write that in, and this would be a 2x squared. 2x squared. So 2x squared. I'm going to give myself a little more room here. 2x squared minus 34. Okay, Now all I have to do is factor the 2x squared minus 34. It doesn't look like anything rational goes into that, and it looks like it factors using the difference of two squares. So let's go to the next, and remember we had to factor f of x equals x minus 2 times 2x squared minus 34. Well, for starters, let's pull out that GCF of a 2 in there. So we have f of x equals, I'm going to write my GCF in front, 2 times x minus 2. That leaves us with an x squared minus 17. I wish that were a 16. That'd be a nice pretty difference of squares, but nevertheless we can still use the difference of squares formula. We're just going to factor that 2. Let's write in the 2 and the x minus 2. And that would factor to x minus the square root of 17 and x plus the square root of 17. Now I know I've completely finished factoring, and this is my final answer because all of my x's are x to the 1 power, and I have no more x squareds. So there is my f of x factored over the real numbers.